This is a second recording for section 12.2 or 12.4. Values that are not exactly 1, 2, or 3 standard deviations from the mean. So remember, we discussed the 68, 95, 99.7 rule that we could find. We knew that 68% of data values fall within 1 standard deviation, 95% of data values fall within 2 standard deviations, but we know that not all data values are going to be exactly 1, 2, or 3 standard deviations away, right? If you have a mean of 70 and a standard deviation of 5, and you want to know what percent of data values fall above 72, well, 72 is not 1 standard deviation away, so we couldn't use that 68, 95, 99.7 rule. So instead, we're going to have to use a different method that involves using a z-table. So what we are going to have to do is find the standard score. Given a specific score, we'll find a z-score or a standard score. And how we do that is we take the data value minus the mean, and then we get that result and divide it by the standard deviation. So if you take the data value minus the mean, right? If you have a data value below the mean and you take the data value minus the mean, you're going to get a negative z-score. So anything over here will be a negative z-score. And then if you take a data value like 80 and you subtract the mean of 70, you'll get 10, and divide by the standard deviation, you'll get a positive z-score. So anything to the right of the mean is going to have a positive z-score, and anything to the left of the mean is going to have a negative z-score. And then, of course, the mean actually has a z-score of 0. Example, if the mean on a nationwide test is 21 with a standard deviation of 4.7, find the z-score for a test score of 30. So again, the z-score is found by doing the data value minus the mean, and you divide that by the standard deviation, which is something that you will need to know how to compute on the test. The data value is, of course, the one that's, and it should say that this is normally distributed, but these types of standardized tests are normally distributed with a mean of 21. Okay, so the mean is 21, and we want the test score of 30, so that's our data value in question is 30. So we can see that 30 would actually be to the right of the mean, so you know that the z-score will be positive. So if you ever get confused if you do data value minus mean or mean minus the data value, right, up here in the top, if you ever forget which way it goes, just look at the curve and decide whether the top should be negative or positive. So the data value is 30 minus the mean of 21 divided by the standard deviation. And again, make sure that you subtract the numerator, get the result, and then divide by 4.7. Right? Don't do it all in one step in your calculator unless you put the top in parentheses. 30 minus 21 is 9, get divided by 4.7. And so that is 1.91. So basically that tells you that the data value of 30 is 1.91 standard deviations above the mean. Right? And so we can see that 30 is not exactly 1, 2, or 3 standard deviations away from the mean, so we can't use that data value. It's 1.91 standard deviations above the mean. So I guess that's to interpret your results, that score is 1.91 standard deviations above the mean. The mean weight of a newborn infant is 7 pounds and the standard deviation is 0.8 pounds. The weights of newborn infants are normally distributed. Find the z-score for a newborn weight of 6 pounds. So we actually have our data value and our z-scores. Remember, our z-score is 0. for the mean. And the data value is the mean of the data set, and it says that the mean weight of the newborn is 7 pounds. And it says find the z-score for a newborn weight of 6 pounds. So you know that since that's below the mean, that this here is what we're looking for. It will end up being negative. So z is equal to, remember, the data value minus the mean over the standard deviation, and the data value is 6. We're interested in for a 6-pound baby, what is the z-score? 6 minus the mean, which is 7, over the standard deviation, which is given up here, is 0.8. So you get -1 over 0.8, and then you'll put that in the calculator, -1 divided by 0.8, and you'll get negative 1.25. So this over here is -1.25. So that means a weight of 6 pounds is 1.25 standard deviations below the mean. And then it says find a z-score for a newborn weight of 7 pounds. Well, remember, it's data value minus the mean over the standard deviation. And the data value is 7. The mean is also 7. And the standard deviation is 0.8. That's given. So you get 0 over 0.8. So that's 0. So that makes perfect sense, because here is the mean for the data set, x, and the corresponding z-score is 0 because it's right in the middle. Student scores, a student scores 70 on an arithmetic test and 66 on a vocabulary test. The scores for both tests are normally distributed. The arithmetic test has a mean of 60 and a standard deviation of 20. The vocabulary test has a mean of 60 and a standard deviation of 2. On which test did the student have the better score? So arithmetic and vocabulary. So for the arithmetic, the mean was 60 and the standard deviation is 20. Vocabulary has a mean of 60 and a standard deviation of 2. So this is your x. So x. Okay. So a student scores, so the score, the data value that we are interested in, is 70 on the arithmetic test and 66 on the vocabulary test. So you can see in both cases, the student scored above the mean. All right, the mean was 60 and the data value and the score on the test was 70. And over here, the mean was 60 and the score on the test was 66. So they scored above average, but right, you have to take into consideration the standard deviation. The standard deviation for the first one is a lot larger than the second one. So we want to know, right, the higher number of standard deviations above the mean, the higher the score. So let's go ahead and compute the z-score. The z-score is the data value minus the mean over the standard deviation. So this one's going to have a z-score of 0.05. So this student scored 0.5 standard deviations, a half a standard deviation above the mean. All right, well, you might say, oh, 10 points, that's greater than 6 points, but you have to take into consideration that the standard deviation. Over here, the data value minus the mean, 66 minus 60, over the standard deviation, you get 6 divided by 2, which is 3. All right, and you can easily see that because the standard deviation is 2, and so obviously 66 is 3 standard deviations above the mean. So 3 standard deviations above the mean. Right, which is a lot higher. So this student did on which test did the student have the better score? That would be the vocabulary. All right. Higher standard deviation above the mean. All right. And if you remember, 99.7% of data values were within 3 standard deviations from the mean. So scoring 3 standard deviations above the mean is very high. Finding the value given the z-score. So IQs on the Stanford-Binet intelligent test are normally distributed with a mean of 100 and a standard deviation of 16. So what is the IQ score corresponding to a z-score of negative 1.5? So since the z-score negative 1.5, or the z-score is negative 1.5 standard deviations below the mean, or just 1.5 standard deviations below the mean, take the mean and subtract 1.5 times the z-score. So we know that the mean is 100, all right? And for our data value, right, our z-score is negative 1.5. So what we want to do is take 1.5 standard deviations below the mean. So we know that the standard deviation here is 16. So we want to figure out what is 1.5 standard deviations below the mean. So 1.5 times 16 will give you 24. So you know that a score of 76 will actually be 1.5 standard deviations, because 1.5 times 16 is 24 points, 1.5 standard deviations below the mean. You know, it tells you this sort of the formula up there, which is what you would get if you solved our z-score formula for our data value. But, you know, you don't really probably, I mean, unless you think you need to memorize this formula, instead you can just think about what the z-score means. Again, we have a mean of 100. And it says, what is the IQ corresponding to a z-score? So here's our x, our z-score of 2.05. Well, 2.05 is up here. All right, z-scores above the mean are positive. Above the mean, so we want to take our mean and we want to add to it 2.05 standard deviations. Again, the standard deviation is 16, so we do 2.05 times 16. So a IQ of 132.8, all right, is an IQ that's 2.05 standard deviations above the mean. And again, you could, if you want to find the data value, right, we're given the z-score and we want to find the data value, which is opposite of what we did in the last slide. All right, you could memorize this formula up here or just think about it. So when you hear, you know, you often hear, you know, in the ACT you scored in the 80th percentile, right? If so what that actually means is if n% of the items in a distribution are less than a particular data value, we say that the data item is in the nth percentile. So a student scored in the 75th percentile on the SAT. What does that mean? And this means that the student scored higher than 70%, 75%. The students scored higher than 75% of all other students that took the SAT. And the last topic in this section has to do with the margin of error. So you might hear statistics, I mean, particularly in election polls, it says at the bottom, you know, the margin of error is 2% or something like that. So, you know, when we report something, there is a margin of error, and it all depends on how large our sample was. So statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening in the population. Often a margin of error is reported, right? We might say, you know, 60% of people are voting for candidate A, but then we gather that information based on a random sample, but we would have to report the margin of error, right? We are only going to focus in this class on a 95% confidence interval. Which has this specific formula given. If n is the sample size, there is a 95% probability that it will lie within 1 over square root of n of the true population parameter. So, right, we're using the sample to estimate for the population, but n here is a sample size, of course, always. All right, so this plus or minus 1 over square root of n times 100%, we need to convert it to a percent. This will give you the decimal, and then you convert it to the percent, is called the margin of error. Add and subtract the margin of error from the given percent statistics to find if it's given, to find the 95% confidence interval. So what this will tell us is we can be 95% confident that the true population parameter lies between these values. So if you see something with a margin of error of 2% at the 95% confidence level, you know, it just means that we're 95% confident that the true number of people that will vote for the candidate is within 2% of what we're reporting. Okay, so we will do one example of this. In a random sample of 1,172 children ages 7 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. So let's find the margin of error. So again, the margin of error, it's a formula that you will need to know, is 1 over square root of n times 100%. And n is the sample size. So that's our 1172. So plus or minus 1 over square root of 1172. And then we need to change it to a percent by multiplying by 100. So if you have the TI-30x11s, you can just hit 1 divided by second function x squared, which is your square root button again. 1172, close the parenthesis and hit equal. All right, otherwise you might have to keep all the decimal places in the square root and then hit 1 divided by that and punch in all the decimal places. That will give you 0.029, and then I'm going to go ahead and multiply that by 100 and press equal so I can do it all in one step in the calculator. 2.92% is the margin of error. All right, and we'll tell you how far that you should round to in your homework. It didn't specify the nearest tenth or hundredth of a percent. So we'll go there. Write a statement about the percentage of children who feel that getting bossed around is a bad thing about being a kid. So this is for a 95% confidence interval. So we can only, if you're interested in other confidence intervals, you can take another higher level statistics course. We can be, or let's maybe so there is a 95% chance that the population percent, so all kids 6 through 14, right? The population, this is a sample, is 1172 children, ages 6 through 14, so the population is all children between 6 and 14. So there's a 95% chance, not change, chance that the population percent lies between. So they reported 17%, so the margin of error is 2.92%. So we take 17 and we're going to add and subtract, right? All this has a plus or minus in front of it. Plus or minus 2.92. So we'll do 17 plus 2.92. It should give 19.92, and 17 minus 2.92. is 14.08. So from the sample, they reported 17%, but based on the sample size, we can be 95% confident that that the population of all kids that believe being bossed around is a bad thing lies between 14.08% and 19.92%. Right? This number 17, of course, is halfway in between those two values. But that is what we need to report, that, you know, we can't be 100% sure that it's 17%, but we can be 95% sure that it will actually lie between those two percentages. There is actually one more slide about other distribution shapes, but I'm not sure why they're not showing up on here. Not all distributions are bell-shaped, are normal distributions. If you look in your notes, you will see there's a picture of, you don't need to write this down because you should see that this type of distribution that's not bell-shaped is called left skewed. If it thins out to the left, that's actually left skewed. And of course, you wouldn't use any z-scores or anything for that because it's not a bell-shaped normal distribution. And this is here right skewed if it thins out to the right. And then you will see a picture of a double peak, a bimodal distribution that looks like this, right, where it has two peaks. All right, so those are some other types of shapes of distributions, which have their own methods of calculating percentages and things.